Now, let us study the variation of fluid pressure with height. So, this is variation of fluid pressure with height. So, what we do? So, here we consider a vessel and such that the bottom things are measured from the bottom. Suppose I say this is x axis and I select this is my x axis and this is my y axis. So, we have liquid up to here. This is denoted as capital H, and in order to understand how the pressure varies with height, we imagine a fluid element that is cylindrical in shape. This is a small fluid element. So, this diagram is a very exaggerated diagram. So, the pressure varies with height, and here there is a fluid pressure P, and so P is the pressure and area is dA. So, P dA is the force. Now, here the fluid pressure changes to P plus dP and the area is dA. So, this is the force downward and the weight, that is dm into g, is acting downward. So, consider a fluid, a differential element along y direction. The axis of this cylindrical fluid element is along the y direction. So, now let us see the equilibrium of the cylindrical fluid element along y axis. So, total downward force we have P plus dP into dA plus dm weight, dm into g, that is weight, equal to P dA. So, we have P into dA plus dP into dA plus this is rho. Now, let us assume that this is at y height and this is dy. You see this exaggeration, this dy is very small compared to y. So, this is an exaggerated thing. So, dm is equal to rho dA into dy. So, dA into dy is the volume into rho is the mass g. So, PdA. Now, PdA cancel. So, we have dP into dA is equal to minus rho dA into dyg. dA again cancel. We have dP by dy is equal to minus rho g. This is how pressure varies with height. Thus the pressure of the fluid decreases with height. So, if we go above, the pressure will become less. So, now how much less if we want to calculate, we can do this by integration. dP will be minus rho g dy. So, suppose initially pressure is P1 and the final pressure is P2, this is H1 and this is H2. So, P2 minus P1 becomes minus rho g H2 minus H1. So, we have P2 minus P1 rho g H1 minus H2. Now, you see, if I want to measure the fluid pressure in a vessel, then generally we do not measure from the bottom, we measure from the top. So, we do not measure things from liquid bottom, we measure things from the top. So, we have to express 2 and 1 H1 H2 in terms of the distance from the top. So, now suppose I denote this height as h, that is from the surface, and I want to know. So, what we will do, that means my H1, the pressure, suppose H1 to H2, H1 is equal to H minus H and H2 is equal to H. So, we will substitute in place of P2. So, we have P2 minus P1 is equal to rho g H1 minus H2. So, P2 pressure at H2, that is here, suppose I say P2 is atmospheric pressure PA. So, P1 is P rho g H1, H1 means H minus H minus H2 H. So, we have thus P atmospheric minus P is rho g H minus. So, P is equal to P atmospheric plus H rho g. Thus, if we have a liquid and we are at a distance h from the surface, free surface of the liquid, then the pressure here is going to be the atmospheric pressure plus H rho g, where H is the depth, rho is the density of the liquid and g is the gravity of the universe, that acceleration due to gravity. Now, let us take some examples to show how pressure varies with height. So, we have a triangular, equilateral triangular, we have an limb that is in the form of equilateral triangle. So, we have a tube, hollow tube, which is in the form of an equilateral triangle in a vertical plane. So, it is a vertical plane and it contains 3 immiscible liquids. So, we have 3 immiscible liquids, 3 immiscible liquids of equal volumes inside a equilateral triangular tube in vertical plane. So, we have 3 liquids. Further the density of the liquids are in arithmetic progression. So, you see how we have 3 liquids. So, this is one liquid that is shown in dotted, and I say this length is x. There is this another liquid. So, we have this liquid up to this. So, this time x will be like this, and next we have this liquid which is up to this. So, this x will be here. So, this is x, this portion x, this portion x. So, we have to determine x. So, determine x. We have to find how much will be the x. Let the length of the tube be L. So, suppose I take this point. So, how to proceed? So, I take a area here, and according to Pascal's law, the pressure here and this side will be the same. That means, the pressure here and here or here and here should be the same. So, let us take 2 points 1 and 2. So, let us take 2 points 1 and 2, and so by Pascal's law law, P1 must be equal to P2. So, this is our idea that I will equate the pressures at 1 and 2, P1 should be equal to P2. Let us see what will be the pressure at P1. So, now let us first see the liquid. Suppose this liquid, that this one liquid has a density that is rho plus d, and you see they are in the liquid densities are its arithmetic progression. So, the densities be suppose rho minus d, rho and rho plus d. So, the heavier liquid will be enjoying the bottom place rho plus d, thereafter this will be rho and the top liquid will be rho minus d density. So, heavier will be at the bottom. So, as you go away you can see the pressure changes. So, now you see we have to equate P1 with P2. So, P1. So, P1 will be, now all heights will be measured from here. Suppose this is x. So, you see here this is x sin 60, x sin 60, sin 60 is root 3 by 2. So, this becomes x root 3 by 2 here to here. Now, this is L. So, this height is, this is L minus x. So, L minus x root 3 by 2 is this height from here to here. This is L minus x, this is L minus x. The total length is L. So, pressure at 1 is the pressure of this liquid plus pressure of this liquid, this liquid pressure and this liquid pressure. So, that constitutes P1. So, we will start with this liquid, that is x by root 3, this is H rho, density of this liquid is rho minus d g, plus, now this is the pressure at this point and this extra pressure will constitute P1. This one again L minus x upon root 3 by 2, its density is rho into g. Now, that is pressure at 2. Now, come to this point. So, here the pressure is for this, that is L minus x. So, that is again L minus x root 3 by 2, this sin 60, sin 60 is root 3. So, root 3, that distance is h and density is rho minus d g, plus this again x. So, this is x. So, this is again x by root 3 by 2, x root 3 by 2, density is rho plus d into g. So, here you see root 3 by 2 g is cancelled everywhere, root 3 by 2 g cancelled everywhere. So, we have x. So, x rho minus x d plus L rho minus x rho is equal to L rho minus rho d minus x rho plus x d plus x rho plus x d. So, you see here x rho cancelled, here x rho and x rho cancelled, here rho d is there, and now you see x d and here x d and here x d, L rho, here L rho and L rho cancel. So, this x d will go this side. So, x d 3 x d. So, now only minus rho d is left. So, d cancel, implies here it is x d and here rho d. So, now here you see this is L rho into L d, it is not rho d is L d. So, L d and here it is L d. So, d cancel, implies x is equal to L by 3. Thus, we see that x is equal to L by 3. So, how now in this example we have seen that how the Pascal's law first we have applied, that pressure at 1 and 2 is same, and next how pressure varies with height. So, here the pressure is the pressure due to this, that is h rho g, that is x by root 3 by 2 h g, and the pressure here will be due to this, that is L minus x root 3 by 2 rho g. So, we equated pressure from this side and the pressure force from this side, and so we got x is equal to L by 3. So, now let us come to example 2, where we have a circular tube. We have a circular tube here, and you see here this time I have two liquids, again immiscible liquids of equal volume, and they are covering half of this circle. So, you see this half of this part is this, and there is another dotted one, another liquid with here. So, we have two liquid of density rho and sigma. Now, it is asked to know what is the angle theta the interface makes with the vertical. So, what is the angle? What is the angle the interface makes with the vertical? So, we wish to calculate this theta. So, this rho and this is sigma, we have two liquids. Now, what we do, again we take 2 points, one point here and another point here. So, again this time I am going to equate pressures of 1 and 2. So, in order to equate the pressures of 1 and 2, I have to know next that what is pressure here. So, you see the pressure here is, you drop a perpendicular here, is the pressure due to this column of liquid, this height. So, you see this is theta, this is theta. So, this total angle 90 minus theta this. So, this angle becomes theta. So, we have r and this will be r sin theta, r sin theta. This is theta, this is r. So, here to here it will be r cos theta. So, this point means from here to here it is actually r cos theta. So, now let us talk about P1, the pressure at one side. So, the pressure at one side is this height is total r cos theta minus r sin theta, r cos theta minus r sin theta. This is H and rho, density rho g. This is the pressure, and this is equal to the pressure at this total point. Now, you see if I extend it, this is theta, this is 90, this is theta, this is 90, and you see I wish to know this angle is also equal to this angle. So, 90 minus theta. So, this angle is theta. So, this is r and this r. So, this is theta, this is r sin theta, r theta sin theta. So, we have P2 as from here to here this height, this is r sin theta, that is r sin theta plus this is r cos theta, that is sigma g. So, g cancel, this r also gets cancelled. So, cos theta minus sin theta by cos theta plus sin theta is equal to sigma by rho. I wish to calculate theta. So, what I do? We use our trigonometric formulas, this plus cos theta plus sin theta is equal to cos theta minus sin theta minus cos theta minus sin theta is equal to this plus rho by sigma minus rho. So, sin theta cancelled, here cos theta cancelled. So, here we have 2 cos theta and here minus 2 sin theta is equal to sigma plus rho by sigma minus rho. So, we implies we have tan theta, I have brought this up and rho minus sigma by rho plus sigma. So, this is the angle the interface makes with the vertical.